of the considerations lead to the same equation. And we clearly discussed about the various aspects of compressibility, incompressibility in terms of the nomenclatures, compressible flow, incompressible flow, and of course, I mean the consideration of density as one of the important parameters in the context of compressibility. Now, as an engineering analyst, given a particular fluid flow, it may be first a bit of a difficult choice to figure out whether you will treat the flow as compressible or incompressible, because in reality, I mean things are all either practically incompressible or practically compressible. In theory, everything is compressible. I mean there is some compressibility. Compressibility may be very small, but there is always some compressibility. So to understand those issues, we will later on have a chapter on compressible flow, where we will see that for practical engineering considerations, we use a non-dimensional number called as Mach number, which is the ratio of the velocity of flow and the sonic velocity, or the velocity of sound in the medium, so to say, and that will dictate whether compressibility effects are important or not. Typically, for Mach number less than 0.3, compressibility effects are not important, and it can be shown like that, and I will show that in that context. Of course, this is a chapter on fluid kinematics, so we will not get much into that, but that is just a passing note. Now, what I want to emphasize here is again something which puts up a gap between what you have studied in school, what you have studied in junior undergraduate at maybe several places, and what is reflected in this equation. Again, I mean from my past experience of talking with students and interviewing students in different forums, if I ask a student that can you write the continuity equation, commonly what the student writes, I mean this is just a statistical observation, is this one. I mean you may well argue that maybe 99% of students in the class will not write this if it is asked, but from my statistical experience, 99% of the students, I mean globally whom I have addressed, will give this as an answer. So the question is that when they have given this answer, they have either learnt it from somewhere, or they are telling it from some perception, whatever it is. And because so many of them are telling this, I guess that this is not wrong. And of course, this is not wrong, and this can be applied. But the broader question is not whether this is right or wrong, but the broader question is where is the connectivity between these two? Because I mean, somebody being asked to write a continuity equation may write this, or even write this, and well, if somebody writes this, you cannot simply say that it is incorrect. But at the same time, it is not what we have learnt as a mathematical description of conservation of mass. So where is the gap between this thing, what is covered mostly very high school level or early undergraduate level, and this one which is also covered in the undergraduate level and more deeply in further studies. So to understand that, the best way of understanding is to take an example. So let us take an example of a fluid flow through something, I mean, which I have made a very arbitrary shape. The only hallmark which I want to keep here is that you have this area of this cross section is a function of x, where x is this. So we want to apply this continuity across the two faces 1 and 2. So this is face 1 and this is face 2. Why 1 and 2 faces are important is because the fluid is entering 1 and leaving 2. These may be simply walls. These are walls. And this is very common. See, any engineering duct, small scale, large scale, will be something like this, where you have an inlet, another outlet, and the others are walls, maybe simple geometry or complex geometry, but walls. Okay. So I have not put any restriction on the shape of this duct. It could be rectangular, circular, arbitrary cross section, whatever. Only thing that you have one inlet and one outlet. Typically, if it's a conical and converging section, it is also known as a converging duct, or if it is having a compressible flow, then it is called as converging nozzle. So now I will write, try to write this equation there. The first we will consider the first assumption, and a very important assumption, that it's a steady flow. If we call this as a steady flow, the major advantage that we will get is in terms of simplification of. So we'll start with this equation, not this one. Right? This is, we will see whether it boils down to this equation or not. But we will assume the one which we have derived, not the one which we have not derived. This is something that books are telling us we have not derived it. So we will neither argue that this is right nor argue that this is wrong, but try to see whether we can reach to that. So the first, if you consider steady flow, and this is very important because then only this time derivative gets to 0. So we will have for that steady flow divergence of rho v. So this is a differential equation in terms of vector differential, but a differential equation which is valid at a point. So let us say that point is this one where this equation is applied. Now we take a small differential volume dv, and to make it applicable, so this is applicable for at a point conservation of mass. We want the mass conservation to be applied over the entire domain, not just a point. So we'll integrate this over the total volume, which is our control volume. This total volume means this total nozzle or whatever you say. So over the entire volume. Now what we will do is we will use something which is known as the divergence theorem. So let us erase this one. Somehow the erasing panel has hung in my top this one panel, so I'm not able to use it, but somehow I will manage. So now if you see one of the major theorems in vector calculus is this Gauss divergence theorem. So what it says is that if f is a vector function, any vector function, right, there is no restriction, then the dot product of f with the area vector. So what is the area vector? So you have to consider a closed surface, and you can take a small area, say ds. So area vector means when you have this small area ds, so it is almost like linear element in this projection, plus there will be a width in a perpendicular to the plane, and that will make the area. So this will have a outward normal. So that is this one. So this is outward normal. So area in a vector form is represented by the magnitude of the area times the unit vector normal to the area, outward normal. That means outward means the surface across which the transport phenomenon, the fluid flow, etc., is taking place outward that surface. So if you integrate this one for this entire surface, remember one of the very basic requirements. See, the problem with understanding a formula and a mathematical rule is that sometimes there are hidden constraints or hidden considerations which we do not remember. We remember this formula. I mean, we may not remember, but if somebody refreshes it, we remember it, because all of us have studied at some point of time in some mathematics course earlier, typically in some first level course on vector calculus. Now, this formula we may remember, and even if you do not remember the formula, if somebody tells you that this is Gauss divergence theorem, you will surely remember it. So this is attributed to the famous mathematician Gauss, who first introduced this theorem. And in fact, this theorem was one of the fundamental bases to develop one of the very fundamental mathematical laws in electrostatics known as Gauss law. So you can see that the impact of this particular mathematical exercise. So this mathematical form we can recollect, but what we may not be easy to recollect, what it may not be easy for us to recollect is that what is this surface? I mean, this is something is ignored in the description. So it has to be a completely closed surface and not any arbitrary surface. The surface which completely encloses the volume under concern. So whatever volume you take, the surface that you have to construct to convert the volume integral to surface integral is the surface that completely encloses the volume. So that is the connectivity between the volume and the surface. Now, some of you may immediately jump in and say that whatever is written here is not correct. Volume will be triple integral, surface will be double integral, etc. You have to keep in mind that these are symbolic integrals of volume and surface. Whether it is double, triple, or whatever, it depends on the coordinate system being used. So this is a coordinate system agnostic approach of writing. So no bias of writing two integrals, three integrals like that. Whatever number of integrals will be required to describe the volume or surface, we will consider that. So now let us apply this particular theorem, considering this rho into V as F. So you can clearly see that the right hand side is this one. So from the divergence theorem, we can clearly say that this is as good as F dot this one. Is equal to 0. So this is from the divergence theorem. Now, in place of F, let us write rho into V. So in this rho into V, what we can say is that we are now describing about actually the mass flow rate through all the surfaces of this volume of the duct. So out of that, the lateral surfaces are not participating in mass flow because there is no flow across this until and unless you put some hole on the lateral surfaces and allow the mass to either get out or get in. But we are not considering that complexity. So we are considering that there is one inlet and one exit. Therefore, if you now convert it to the integrals on the respective surfaces, only for surfaces 1 and 2, it is non-zero. Otherwise, I mean, It is non-zero in a sense that it is contributory. But for all other surfaces, it is not contributory because there is no flow across the other surfaces. So simply you can write for the surface 1 plus this is equal to 0. Now for the surface 1, let us say that all the flow is occurring along the x direction. How that is possible? It is possible, say this cross section and this cross section, these have the normal directions are x. So if the normal directions of the cross section are x, no matter whatever is the velocity, 2-dimensional, 3-dimensional, 1-dimensional, but the velocity component along x, that is u, will only contribute to the flow rate. This we have seen in one of our derivations, that because the flow rate depends on the component of velocity perpendicular to the plane across which the fluid is flowing. So for calculation of the flow rate, only x component of velocity is important. It doesn't mean that other components are there or not there. It doesn't make any commitment for that. What it simply tells is that for calculation of the flow rate, only the x component is important. If the surfaces are oriented normal to x. So that is what is our second assumption, that all the flow surfaces are oriented normal to x. I mean one particular direction, and that direction let us call it x. Now, therefore, so the first integral, so rho in place of v, it will be x component of velocity. I mean, you can write the other components also if you want, but where the other components will not be important is when you calculate the dot product. The dot product is the outward normal vector. Now look at the surface. So if you have this surface, its outward normal vector is in which direction? It is in minus x direction. So that means it is minus I. Okay, and ds. And let us say the total area of the surface is A1 and the total area of this surface is A2. Okay. So it should be quite clear that how this boils down to this. You have the velocity components entering the section 1, and of course these are local. That means at one point, and it can vary across the cross section. Not that it is same at all points. It can, this u is a function of whatever x, y, z along the cross section. But the normal to the section is minus I. So this is for the surface 1. Similarly, for the surface 2, so let us write that plus. So let us integral of rho. So rho. Then you have this again ui plus whatever. Now for the surface 2. Then the normal, see, outward normal to the surface 2 is positive x unit vector. So that is I. So sum total of this is 0. So when you have sum total of this is 0, so there is a dot product here. So dot, very, very important. So now, okay, let me free up some space here. Write the simplified from here. So out of this dot product, only the x components are important because other dot products will be 0 no matter it's there or not. So rho u ds at surface 1 minus plus rho u ds surface 2 this is equal to 0. Okay. So now what we will make is we will make certain assumptions. So far we have made two assumptions. One assumption is steady flow. The second assumption is that the surfaces across which the fluid flow is occurring, those surfaces have one common normal direction, which is x. These are the two assumptions that we have. The third assumption that we will make is that over those respective surfaces, the properties are uniform. That means when the density may vary with x, but at a given x, that is at for a section A1, the density is uniform over the section A1. So it doesn't mean constant density. It only means uniform locally over the surface. So why we are making that assumption is because that assumption will enable this rho to come out of the integral over those respective surfaces. So then you are left with a generic form of integral. This is like integral of UDS. So now if we define something which is called as average velocity, this is a very important parameter in fluid mechanics, and those of you who have done a first course on fluid mechanics know about it. So it is simply integral of UDS over whatever is the area divided by the total area. Okay. So what it physically means is that, see, this U will vary over the cross section. So the total flow rate, volume flow rate, is this one, integral of this over the cross section. Now, had the U not varied over the cross section but been uniform, then the flow rate would simply be that equivalent uniform, that is which is not varying with the cross section, times the area. So that equivalent uniform velocity is called as average velocity in a physical sense. So in place of integral UDS, you can write U average into A. So that means this equation will boil down to minus rho 1 integral UDS over 1 is U average 1 into A1 from this formula. So this, you just multiply these two, plus rho 2 into U average 2 into A2. So this is equal to 0. So now if we just write it in a reorganized form, we will get rho 1 A1 U1 average is equal to rho 2 A2 U2 average. Okay. A very special case is that when rho is absolutely a constant. So rho is constant. If rho is constant, then it leads to A1 into U1 is equal to A2 into U. Right? Rho constant means you have cancelled this one. Or even if rho is not, so now I will ask you some questions. So let me just stop the discussion here for the time being, and let me put up some questions as sort of brain teasers. So the first question that I intend to put up is, let me just write it somewhere here. Number 1, is it necessary for the final equation to hold true that rho is constant? For this equation to hold true. Yeah. Can any one of you, from the common sense based on the derivation that I have just made, without any prejudice, without absolutely any prejudice of what you have learned earlier, based on this derivation, what I have just done, can any one of you make an attempt to give an answer to this? No prejudiced answer. Answer only based on the derivation, because mathematically seeing is believing. Can any one of you make an attempt? Am I audible?
Yes, sir.
Yes. So any one of you make an attempt. I am not closing the board, so I am not able to see your name, because it has apparently hung. So if I close the board, I will try to close the board. Entire MS Teams session will hang. So I am not taking that chance. So I cannot see your names. But you can just tell.
Sir, I think only the density at and the phase where it is and fluid is entering and where it is leaving the control volume is should be equal. In between, we have not considered.
Excellent answer. Excellent. Very good. So, see, rho equal to constant is therefore only a prejudiced thought, right? I mean, it is not having any big basis, because we just wanted to cancel rho 1 and rho 2, right? Some way to arrive at this one. So we can cancel rho 1 and rho 2 simply with one of the considerations, that rho 1 equal to rho 2, but in between it could have varied in whatever way it wanted. So rho equal to constant need not be a very binding compulsion. Now we have started this derivation. So I will put up some paradox to you. I mean, which will be a brain teaser exercise for all of you. So now we have derived this. So I mean, this much we all agree from simply the algebra that has been done, that if rho 1 is equal to rho 2, that is good enough to give rise to this equation. Now I will just try to arrive uh, through an alternative approach by considering incompressible flow from the very beginning. Okay. So not so here we started with what? Can you remember? We started with unsteady flow. Steady flow. Right? We did not start with incompressible, compressible, etc. So we started with steady flow, right? So that is how the first rho dependent term, time dependent term in the continuity differential equation was 0. So with that only we started this derivation. We will start another approach of similar derivation. Now another example. So let me just clear this place. So in this example, we from the very beginning considered incompressible. And as we have learned in kinematics, and in fact, just to keep in mind that we are actually in the chapter of kinematics and not anything else. So whatever is coming up here is from some considerations which are related to kinematics in some way or the other. So incompressible flow we most fundamentally derived as a kinematic constraint. So the kinematic constraint of incompressible flow is simply the divergence of velocity equal to 0. Okay. So now let us consider this incompressible flow and try to apply this to this one, this problem, I mean this physical picture. So we'll have a volume integral over the entire volume, and that is it. So just like the previous thing, same divergence theorem etc. we will apply, but the rho factor has not come. So this will straight away lead to A1 U1 average is equal to A2 U2. Straight away. I mean, exactly same derivation, so I'm not wasting time by repeating again. Only the rho factor is not there. So this will come. So we have seen in one approach, this is coming with incompressible flow, no restriction on density, but incompressible flow, and this being arrived at with certain restrictions in density, but the final equation being the same. So the question is that one being arrived at with certain restrictions of density and other with no restriction of density, final equation same. So are they actually equivalent or not? Because in one case restrictions were there, in another case the restrictions were apparently not imposed. So is there any contradiction because of these two? Again, can any one of you try to explain this? So this is example 1, this is example 2. So what is there any contradiction between the way in which the mathematical steps are drawn are done for the two examples? Because in one case some considerations for density starting from the beginning steady flow to the last step were required. For example 2, no consideration of density was, but final equation same. So where is the contradiction, if there at all any contradiction? Just can any one of you speak out?
So both are valid in the end conditions only. 1 and 2 only. And in between the
No, this is no. This is I mean we are writing at 1 and 2 only. I mean not that we are writing at other. No, of course both are valid mathematically we are seeing, but my question is that in one case to establish the validity, some constraints on density were imposed. In another case, example 2, no constraint on density was imposed. So the final take home is that is any constraint of density required or not for this equation to be valid?
Sir, in example 2, density will be constant always, but in example 1, the density will be constant only at phase 1 and phase 2, that is surface 1 and surface 2.
This is actually that gap of understanding that everybody has. I'm glad that you told it in words, but what you are saying is actually is not correct. So in example 2, we
Sir,
do not
shall I try?
require. Yes, any one of you can tell.
Sir, though both the equations arrive to be same, but in case of the first example, the change in, because at only section 1 and 2 the density needs to be same, but in between it has to be some other function. So
No,
that
it has to be. I mean, it may or may not.
May or may not be, but that will be compensated within the volume between those two surfaces.
So in example 2, you are not allowing that.
No,
density variation.
the density variation is not there.
Not okay. Again, you see this. This is actually the same statement that your friend just earlier made. So actually, this is not correct. So if you see, this is where that insight is important. I mean, more you speak out, more even I will realize what the gap is. It is not your fault. I mean, all of you are very sharp and very intelligent, very bright. It is somehow the education which has not prompted you to think in that way, and you only have learned how to solve the differential equation for solving some problems. So try to now make an analysis. See, if you recall that when this was derived, one of the corollaries of the derivation is that the total derivative of density is 0. Right? Why? So this is for incompressible flow. But the general continuity equation, that is the partial derivative of density with respect to time plus divergence of rho v equal to 0, is true for all flows, no matter compressible, incompressible, whatever. Now, on the top of that, if you apply this incompressibility constraint, you will get the leftover, the remaining terms, total derivative of density equal to 0. So, although we have not explicitly talked about density in example 2, example 2 is premised on not constant density but on this. Okay? So I hope all of you will agree to this, because this is something which I have derived in details in the previous class. And in fact, example 1 is one such reflection where, see, what is this? So total derivative of density is the unsteady plus this one. So the unsteady term 0 we considered steady flow, and that grad rho, that is the special change of rho as the fluid is leaving and entering. So when the fluid is leaving and entering, the special change is calculated across 1 and 2, and that is also 0. Right? And therefore, this constraint is actually satisfied by the specific example of 1. So both example 1 and example 2 are based on certain restrictive considerations of density, but the restriction in the most general sense is represented by this, not constant density or anything else related to density, but in the most general form by this. Okay.
Excuse me, sir.
Yes.
Sir, if grad rho is equals to 0, does that mean it is a much stronger condition than rho dot n ds is equals to 0?
No. I mean, see, you have to keep in mind that this is a differential equation, and I mean, whatever you write equal to 0 or not, these are differential ones, and this is called as integral approach. So the difference between differential and integral approach, see, how do you arrive at the integral approach? You arrive at the integral approach by integrating the differential equation over the entire volume, but making the result applicable only across those spaces where there is fluid flow, and that is obvious because at all other places you have velocity terms equal to 0 where there is no fluid flow, and therefore the integral equation, when the differential equation is integrated, it looks to be less restrictive because it doesn't care about what has happened all inside. Right? Inside, I mean, so many things could have happened. It only cares on whatever is there at the surfaces across which fluid flow is taking place. So that makes the integral approach looking to be less relaxed. Right? But the integral approach that we have followed, that we can follow directly from the incompressibility constraint also. So what it means is that the special restrictions that we have put up for example 1 are little bit less restrictive than this general thing, right? This
Yes,
general
sir.
thing is much more restrictive. So we can relax that a little bit more by putting two specific restrictions only. Number one, steady flow, and number two, locally the densities are uniform over the sections 1 and 2, and those values are equal. So with just these three you know, less restrictive considerations, but these three considerations together satisfy this, no doubt about that. But now there could be other conditions more restrictive also that could satisfy this, but not required. With relatively less restrictive conditions, with the three considerations one after the other, we could arrive at this one. But in a more general way, with several other conditions also, I mean, that could have been valid. All those conditions would satisfy this total derivative of density. Okay.
Thank you, sir.
So I think that this should give you good insight. I mean, that is what I'm trying my best to do. I mean, I could have just passed say 2 minutes to tell this, because this is something what all of you believe that you have learned so well. Now, so I mean, the discussion on this is not yet over. I mean, so to say, the climax is still left, and what is left is that you are in the junior classes, you are writing A1 V1 equal to A2. In fact, with that we started. So I would not say that whatever is taught in higher school is wrong. But what I can simply tell you is that it gives you an incomplete knowledge in your mind, and if you take it as the final knowledge, you will suffer from the lack of fundamentals through your entire stage of higher learning. So when you say A1 V1 equal to A2 V2, what comes to your mind is normally the subscripts 1, right, and 2. So this is like a magic formula that you tend to use. But ironically, you see that there is nothing called as area at 1, right? Area of the point 1 rather, and the point has no area. So whenever you are saying A1 and A2, actually you are not meaning point 1 and 2. You are meaning area A1 and area A2. So the question is that when you are writing V1 and V2, knowing fully that the velocity is varying over the cross section, right? In a real pipe or a real engineering duct, you have the velocities varying like this. So at the wall 0 and then center line maximum like that. So you do not definitely have anything which is a V1 universal V1. That means V1 over the entire A1. Okay. So since you do not have that universal V1, then what is this V1? So if you now recall that just now we derived the formula A1 U1 average is equal to A2 U2 average under certain restrictions. Let us say that all those restrictions are satisfied. So under those restrictions, what is the meaning of this U1 and U2? These are simply the average velocities over section 1 and 2. So these V1 and V2 are no more, velocities at some identified points. These have to be recognized no matter whatever symbol you use as average velocities over the respective sections. This is very, very important. But in many of the engineering applications, people consider this as velocity at points 1 and 2 and live with it, and still it works. Can you tell why? How that magically happens? Any one of you? So I will give you an example before hearing from you. This kind of discussion is very important. You open yourself up. Let me know whatever you think about it. Doesn't matter it is right or wrong. It is much better to express this rather than keeping a wrong thing in your mind for your entire life. I mean, doesn't matter if some of your friends will never speak out, and you may think that you are doing a foolish act by telling a wrong thing. But I will appreciate if you speak out, because that is how we can discuss. And my job as a teacher is not just to give you some sort of typecast lessons by reading from books. My objective is to bring a clarity and correctness in your conceptual understanding. So I am just putting up an example which all of you who have gone through a first course of fluid mechanics in engineering will be familiar with. Those who have not gone through also is, I mean, I'm just giving it as an example. Don't think that I'm giving any bias to those who have studied it earlier. In fact, I'm giving it a negative bias to those who have studied it earlier, because I want to show that how it was wrongly done. So let us say that so let me write it like that: a problem of undergraduate engineering fluid mechanics. So you have, let us say, 2 points. Let us say a nozzle or whatever, I mean some, and you have a streamline. A streamline like this. We have already defined a streamline, so let us say we have a streamline like this. On the streamline, there are 2 points, 1 and 2. Okay. So on the streamline, there are 2 points, 1 and 2. So the problem may be that you are given the pressure at 1, you are given the pressure at 2, and let us say you are given what more. So you are given the pressure at 1, the pressure at 2, and maybe area of 1, area of 2. You have to find out what is the rate of flow through this. Rate of flow means expecting in units of meter cube per second or something in this dark torch. Basically, volumetric rate of flow, not mass. And it is given density is constant. That much simplification is. So can any one of you tell, given this as an undergraduate fluid mechanics problem, how do you solve this problem? Now you can keep all your any one of
By the help
So
of Bernoulli.
by applying the spherical energy
I mean, one of you speak, because I mean, do not speak multiple. One of you, any one of you. I have no bias. I mean, whoever starts first.
so by applying this Bernoulli equation here.
Okay. One by one. So whatever you say, I will write so that it becomes understandable to everybody. You have to recognize one thing in this class. You have many students from physics and mathematics who have actually never done an engineering fluid mechanics course, and therefore I mean, we should not make any sort of prejudice to that. So we should write it slowly and carefully, so that they will also understand what we are meaning here. Let us say, okay, the first thing you say Bernoulli's equation, right? And I mean, it's all right. I mean, that is what we do to solve this problem. So you have told you have been absolutely spot on. So what is the Bernoulli's equation that you write? P1 by rho plus V1 square by 2. Then plus
H GH
G into H1. Right?
yes, sir. Assuming the flow to be steady.
Okay. Now, I mean, let me ask a first question to is there anybody in this class who has never come across this equation? Anybody? I mean, it doesn't matter. If you have not come across, you tell. So I believe that no matter you have come from physics, engineering, mathematics, this is what you have studied, because this is actually being nowadays taught in high school. I know, very senior high school, but high school. So everybody is familiar with this, no matter what branch you have later on followed. So this is the so-called famous Bernoulli's equation. Right? And those of you who have gone through a first level of engineering course will have a little bit of deeper understanding and will say that there are certain restrictions behind writing this, and one of the restrictions we have satisfied by considering 1 and 2 on a streamline. Right? Anything more as a restriction? I mean, you can continue. Whoever was telling.
In visit.
So viscous effect is not there, right? So we are assuming that there is no. So in simple terms, there is no viscous force. Right? So in viscid flow, but that's a technical term. So no viscous force. That means viscosity is not important in having a resistance force on the fluid. So I mean that is why no viscous resistance is being put up. Anything else?
Irrotational flow. Assuming it to be irrotational.
Do not bring into that. If we are considering a streamline, irrotational is not
Streamline.
So we have a streamline already, and on the streamline we have taken 2 points. We have considered no viscous force. Anything more is required to make this satisfy for this problem. So one is this one. Rho is the locally constant.
Incompressible.
Let us be a bit more. I will not want to bring in compressibility or incompressibility here, but what we can simply say is that we can apply it for rho equal to constant, no doubt about it. Why I am telling this is because the problem statement itself says rho equal to constant, right? I am trying to solve this problem in an undergraduate approach, right? So this rho equal to constant equal to this rho, that is what I have put. So within that restriction, this is just a simple mechanical energy conservation with no dissipation because viscous force is not there, right? That is the equation. So we are applying this between the points 1 and 2. So in this equation, what is given in the problem? I mean, whoever was telling you just continue. So I'm assuming you are representing all the students who have gone through this undergraduate course. So tell what is given. So in this equation, what is given?
Sir, H1 is equals to H2.
Okay, H1 is equal to
pressure.
H2. Yes. So this is fine. And this is a horizontal nozzle, or even if it is little bit tilted, 1 and 2 are so close that the difference in potential energy is not that important. So we cancel it from practical terms. Then P1 is given, right?
Yes, sir. P1, and P2 is also given.
So the unknowns here are V1 and V2, right?
Yes, sir.
And so you require one more equation because you have one equation where you have 2 unknowns. So what is that other equation?
So continuity
Continuity.
equation.
So that
A1
A1 V1 equal to A2 V2, that famous equation that I was talking about. I mean, famous for solving undergraduate problems. So A1 V1 equal to A2 V2, right? And what is known here, A1 and A2 are known, right? So this will give you another constraint on V1 and V2. So these coupled equations, if you solve together, will give you V1 and V2, right? Two equations, two unknowns, V1, V2, and then the volume flow rate is equal to, that is, if you say Q equal to A1 V1 equal to A2 V2. So if you know A1 V1, A2 V2, etc., this you can calculate. So this is the problem solving, right? So do any one of you disagree that given this problem at the undergraduate level, you would have not used this approach for solving the problem, but would have used any other different approach? Any one of you would say that this, or all of you will more or less agree that given this problem, this is how you would have solved the problem to come up with the final answer? I mean, anybody disagree?
Sir, in Bernoulli's equation, V1 and V2 are not average velocity, but in continuity equation, V1 and V2 are average velocity.
That's not right. I mean, now we recognize that, but given to solve this problem, you would have used this approach only.
Yes, sir.
Not?
In undergraduate, I would have approached this.
You would have approached this, right? And you would have got the correct answer. I mean, yes, answer will match with it, whatever in a book that you have studied, which all of you have thought like a Bible, or whatever, Gita, Bible, Quran, whatever. I mean, whatever is your religious book, I mean, whatever book you have studied, you have considered that as a religious book, and that book will solve the problem invariably in this way. Now, the interesting thing is that the solution that you have come up with in most of the practical engineering applications will be more or less correct. If viscous force is negligible, more or less correct, but the method of solution is fundamentally wrong. So this is a beautiful example, but the method is wrong, but the final answer is correct. And through your all practice of competitive exams, starting from JEE, GATE, etc., you have learned so many of these ways of coming up with an answer where the answer is correct, but the method is fundamentally wrong. So this is one such burning example in fluid mechanics. So now, can you tell why the answer is more or less correct of what you may observe in practice, though the method is fundamentally incorrect? Any one of you? Any one of you? Any idea? It's a peculiar situation where the method is, we can understand, one of your friends have rightly pointed out that these are, points 1 and 2, but these are, sections 1 and 2. So these will be actually average velocities. But we are not using average velocity because we are just calculating V1, V2, whatever. Because this is not average velocity. This is velocity at a point.
Sir, point 1 and 2 may be located anywhere, not necessarily in the same streamline. So as we are considering the point 1 and 2 in the same streamline, this equation gives the correct result.
No. I mean, the point is not whether they have to be located on the same streamline or not. That we will discuss later on. But the point that we have to recognize is that they are still points. So in equation, the first equation, 1 and 2 are points, whereas in the second equation, 1 and 2 refer to areas. That is the primary contradiction, not whether on same streamline or not. That you have to first recognize.
Sir, if the duct is thin enough, then maybe it can be done.
See, I mean, most of the practical engineering flows for which this is applied are mostly, for large scale systems in what run in industry. So they are not really thin enough. They are actually, on the other hand, very long and diameter wise also large. But still,
So
this may be applicable.
there are no viscous forces, so there is no slip condition at the boundary, and
So
velocity
where does slip come into the picture here?
on the profile, the velocity profile at a given cross section.
No, I mean, but I mean, why? I mean, so this is, I mean, this I do not understand. Where is slip important here?
If the profile is not, if there is a no slip boundary condition, the profile is like a parabola. But if there is a slip at the wall, maybe at a given cross section at all the points, the velocity is a constant value. So that
Let
the
me
average.
just okay. Let me put up a different practical example. Again, I mean, these topics we will cover later on, but I am trying my best first to erase the wrong education that you have learned over the years, and then I will give you new education. So imagine you have a pipe like this. So I am giving you two examples of velocity profile. That means if you draw velocity vector, how it is varying over the cross section. So one of the examples is like you have, so if you draw a vertical line and you draw the velocity variation, something like this. In another case, you may have the situation like this. Still, the velocity at the zero at the wall is 0, and then but the remaining more or less over the entire section, on an average, uh, taking away the statistical fluctuations, on an average, this is more or less uniform. So, what are these practical situations? So, this is the so-called classical
The one on the
laminar
left is
flow,
Poisson. The other one is
laminar flow, and this is turbulent. I mean, this is the first hallmark. See, all of you learn a subject through lot of theories, lot of mathematical equations, and that is why things are all jumbled up. So, if you are given a visualization of a simple pipe flow, where there is a pump which is driving the flow through a pipe, and the velocities are measured at a given location. And in this case, in turbulent flow, because there are lots of fluctuations in the flow, so this is a statistical averaged plot of the velocity vectors across the section, and this is just no question of averaging, because here everything is smooth, so no question of averaging. So in turbulent flow, you see this because turbulent flow ensures that there is such a lot of inertial effect in the flow that there is vigorous mixing in the flow. And because of vigorous mixing, there is a homogenization of velocity across various fluid layers. And that makes the velocity statistically almost uniform, except at the wall where it has to be 0. On the other hand, that kind of intermixing, strong intermixing between various layers, because of very much less dominance of inertial effects, is not there in the laminar flow. And because it is not there in the laminar flow, it is the velocity is like this. So now one of the great advantages of putting up this kind of flow in this problem solving framework is that because the velocity profile anyway is more or less uniform over the entire section, if this is the point 1, the velocity at point 1 and the average velocity over the section 1 are more or less the same because of the uniformity. So although this has to be average velocity fundamentally, but we are putting a local velocity at some point 1, we are getting rid of the situation simply because that practical engineering situation in industry is a turbulent. I hope you have got this point. So this is what I say is ignorance is a blessing. So if you know less, you can solve a problem hiding your ignorance, and you can solve a problem faster. If you know more, you will try to think and think and think whether the mathematics that you are putting up, whatever are the assumptions involved, are consistent with whatever is happening in real, in physical reality. Okay. So of course, there are several ways of accommodating this this anomaly between use of velocity at a point and velocity at a section here, and how that is accommodated. Even in undergraduate fluid mechanics classes, it is done in a little bit of gross sense, but it is correctly done. So there are two corrections made to the equation. I mean the so-called Bernoulli's type of equation. One correction is number one, you are multiplying this with a factor which is called as kinetic energy correction factor. So the kinetic energy correction factor alpha, it see what this term physically represents is kinetic energy, but the kinetic energy is not uniform over the entire section because of the velocity variation over the section. So what is done here is that to accommodate that, I mean you now consider V1 average and V2 average. So V1 average is that U1 average in terms of our derivation, and V2 average is U2 average. So if you use the average velocity, then average velocity square by 2 will not represent correctly the kinetic energy because the velocity varies over the entire section. So to accommodate that, a correction factor alpha is multiplied with it, so that the correct kinetic energy is represented, although the average velocity over the section is used. So the kinetic energy correction factor can be theoretically calculated for a parabolic velocity profile, and for parabolic velocity profile you can calculate this later on. It is roughly about this around 2. So see, it's a 100% error if you consider this as equal to 1. But for turbulent flow, it is very close to 1, and that is where you get rid of it. But in reality, there is another very important effect, which is viscous effect, which we have neglected. So to consider the viscous effect, what you do is that in the right hand side, you consider another term, which is the energy loss due to the viscous friction. This we will study later on. So the energy loss is accommodated due to the viscous effect. So starting from the simple thing, you can actually represent a practical problem using the same simple equation by making certain corrections. But even without that corrections, the equation may hold for certain cases like this case, which maybe for our ignorance we do not appreciate, but still apply for solving that problem. So I hope this was this little bit of explanation was interesting and useful, typically in the context of whatever you have learned in the undergraduate level. Now I will put up another contradiction. Do any one of you have any observation on question till this? So if not, okay, you have a question. Yeah. There is a noise, so I cannot hear your question. So, just, yeah, please repeat the question. Can you please repeat the question? Anyway, so let me put up another contradiction. So when we apply the continuity equation for a nozzle, I mean this many times you have solved again in the undergraduate problem solving. So similar this type of thing. Forget about density, say density is constant. So one of the assumptions, key assumptions that you have made is one-dimensional flow. So in reality, is it one-dimensional flow or not? Number one. Number two, even if it is not one-dimensional flow, can we apply this? So I mean, now we are committing A1 B1 average equal to A2 B2 average. So the first question is, in reality, is this one-dimensional flow? Second is, if not, can we still apply this? Any one of you?
Sir, it is not one-dimensional flow, but as long as the like flow velocity direction is in the I direction, we can probably apply this.
Yes, but if it is not one-dimensional flow, or say one-dimensional in the sense that if there are say multiple velocity components u, v, and say w, forget about w at least just 2 dimensions minimum. So then now you have this along the I cap, this along the j cap.
So if the I cap is much more than j cap direction, if the velocity in I cap direction is much more than in the j cap direction, we can probably apply this.
Any other observation before I give an answer to this? Anybody else who want to?
So the continuity equation will be A1 U1 is equals to A2 U2, like in this case.
Yes, that is what I have written. I have just used 2 different symbols. I want me to use U in place of V. I will use that. Right. So I mean, same thing. I mean, I just used different symbol for the same thing. The question remains the same. I have just changed this.
We can consider cylindrical coordinate system and
no question of any coordinate system. This is a physical device.
Only I component
first of all, can you say, I mean, let me just give you an example. See, a little bit of, say, distractor as an example. Let us say the fluid is entering here with a uniform velocity of 1 meter per second. That means somehow you have managed a source of uniform velocity with which the fluid is entering, and all along x direction. Okay. And the remaining, I mean, you do not have any control on your hand. This is what you have control. That is, by some control, external control, you are having a statistically uniform velocity u 1 meter per second with maybe some random fluctuation which statistically you neglect. It's very small fluctuation. On an average 1 meter per second uniformly distributed entering along x through this section, and it will leave in some way across this. How it will leave we do not know. It is up to the fate of the fluid.
Is it something like so since we assume that the velocity is entering at one entirely in the x direction, that it will leave two in entirely the x direction, and for one we consider.
I mean, how can we have that prejudice? That is what I am saying.
Probably for fast velocities it won't, but if it's slow enough, we can assume it will again become sort of uniform.
See, fast slow is something which is very, I mean, which is what I can say is very relative and is subjective. So whatever you say as fast, I will say as slow. Right? I mean, if you are thinking about a micro channel, 1 millimeter per second is a dead fast flow, because typically we are considering there as some micron per second type of. So fast or slow is very relative, very difficult to say. So so I will not get into the fast and slow. So only thing I will tell, I mean, just as an additional constraint, that it is, I mean, it is, I mean, let us forget about the third dimension. Let me just complete the assumptions which will help you actually. So forget about the third dimension, it will just complicate. So let us assume that it is just the domain is a two-dimensional domain, the physical domain, and it is incompressible. And incompressible flow is quite clear because we have used this, right? But 2D is 2D is not obvious, that I have told that the flow may not be 2D, but the geometry is 2D. That means you can have a, say, cylindrical nozzle, something like that. Okay. So now let us try to analyze this before giving an answer. So I will not give an answer, but my analysis will actually tell you the answer. So for two-dimensional this thing, I mean, let us assume that it is two-dimensional, not one-dimensional. No restriction. Geometry is two-dimensional, flow at the most will be two-dimensional. So the divergence of velocity equal to 0 for incompressible flow, that will boil down to this one, right? For u and v are the velocity components along x. Okay. Now tell one thing. This is 1 meter per second. Just consider some section here. Even if it were uniform, uniform, because I have shown you example where it could be more or less uniform, like in case of a turbulent flow. Even if it were uniform, will it here also be 1 meter per second or not? Can any one of you tell?
If we ignore viscous losses, then it will be more than.
I mean, no question of viscous loss. What I am saying is that let us take the typical example of a turbulent flow. Okay. So turbulent flow, say in a nozzle, is a very practical problem, and then here also it will be locally uniform, almost, except neglect the wall effect. I mean, but more or less uniform. But will this also be 1 meter per second or not? That is my question.
It will be more than 1 meter per second.
It will be more than 1 meter per second, right? Because simply you have to satisfy the continuity, flow continuity, right? No matter viscous, inviscid, forget about that. Flow continuity is a fundamental thing. So 1 meter per second into this area must be whatever it is into the smaller area. So area is smaller, so this has to be greater than 1 meter per second, right?
Yes, sir.
So now, if you imagine that how, say along a horizontal line, u is varying. So you have a value of u here, 1 meter per second. Here you have a value of u with change in x. Simply change in x greater than 1 meter per second. Therefore, you have this one, right? Not equal to 0. Because u is a function of x. We have just now proven. Even in the extreme case that it is locally uniform. Otherwise, it will anyway be there. Even in the extreme case, it is locally uniform. You will have a change of u with change of x. Right? All of you agree to this? So if you agree to this and the sum total of these two has to be 0, then this also has to be not equal to 0, and in fact this is, if this is plus a, this has to be minus a, because sum total has to be 0. Okay. So you have a variation of v with respect to y. What is that y? Y is the direction perpendicular to this. So a variation of v with respect to y means that you will have a variable y component of velocity and also some x component of velocity with varies. So let us say you have a x component of velocity. Let me just draw some vectors. So x component of velocity, say first small, then bigger, like this along x. And y component of velocity, so if this is positive, then this has to be negative. That means v will decrease with y. So you have this v this one, then decrease, at the wall it will be 0. So in that way, you have both x component and y component, and they are variable. So actually inside the nozzle, maybe at some location you could have a circulation type of thing, right? I mean a local circulation. No matter if it is, even if it is circulation or not, first of all, one-dimensional flow is not correct. No matter how simplified, even if it is locally uniform, it cannot be one-dimensional. So the first answer I have given. The second answer is that now that we have understood that it is not one-dimensional, can we still apply this? See, the beauty of application of this equation is that we do not have to bother about what happened throughout internally inside this nozzle. We only have to bother because this is obtained after integrating the continuity, the integral form. So only at 1 and 2. So at 1 and 2, if first of all, it doesn't also have to be one-dimensional at these locations. This is very important. I mean, this you might think it has to be. It doesn't have to be. Why? Because let us say, let us take an example. Say inlet we have fixed, but outlet we have not fixed. So let us say outlet we have no control. It is moving out, with a random velocity, and it may. So now this random velocity will have some x component and will have some y component. So whatever is the vector, you can decompose it into some vx and vy, or u and v. So out of that, the vy will not contribute to the flow rate because it is perpendicular to the area, and perpendicular to the area means its vector and the area vector dot product is 0. Whereas only the x component will matter in the flow calculation. That means even if it is a two-dimensional flow, the average velocity is to be calculated only based on the normal direction to this area. And in that way, doesn't matter one-dimensional, two-dimensional, three-dimensional, so long as we take the appropriate component of this velocity which is perpendicular to this, we can apply this. Okay, so see, these are certain very compelling knowledge gaps. We believe we know, but actually we do not know. And this is a very dangerous state of education. If we believe that we do not know and we do not know, it is fine. But we believe we know, but we actually do not know. And this is what I wanted to clarify upfront. So let us wind up today's discussion. I didn't move much further in putting up a lot of theory, but I believe that this kind of discussion was useful. If you have more questions, you can put up. We have about 5 more minutes in the class. Otherwise, we will just wind up and continue this on the coming Thursday. So any one of you, because I tried a different approach, and this is a very drastic approach of teaching. I mean, but it's a bit different from what I do for relatively junior classes, because there all those things are taught as new items, and here these are erasing items from whatever previously you have studied. So if you have any observation, you can tell. So any one of you, any question you have? If not, let us just close this class, and we'll meet again on Thursday. Thank you very much.
Thank you, sir.
Thank you, sir.